So reactions are amazing. We take for granted that they happen like that, but we've been talking about reaction rates. So it takes a certain amount of time for reactants to go to form products. The other thing about reactions is oftentimes, and I alluded to this before, there are behind the scene things happening that you can't pick up from the overall reaction of interest. So those things that are happening behind the scenes are actually little baby steps to get your overall reaction of interest. Okay, so they add up to be what we call a mechanism, a reaction mechanism. Now, sometimes, and I'll be very often, sometimes it's possible that a reaction just occurs in one little step, okay? But more than likely, there's multiple things going on behind the scenes. So these things behind the scenes are called elementary steps, okay? A single step in the overall mechanism to get us our chemical reaction of interest. So what we'll do, and you remember how we kind of added up? We've added up equations before. So again, we'll add up equations to get our overall reaction of interest. Our elementary steps add up together, okay? So there's this term called molecularity. Now this is where this topic actually, I cringe a little bit because I'm building up to, before I get to what I cringe about, how do you guys come, how have we talked about getting the reaction orders? That's the superscripts. How do you get your reaction orders? By slope, right? Slope of, like, I think that was time concentration data, exactly. And my point was going to be time concentration. You did a run, you literally did a run, and you got the time concentration data. Other ways you can get the reaction orders, that's one way. They like the units of K gives you a reaction order. Yeah. Anything else? Remember, how about way back at the beginning of the unit when we talked about, like, if it doubles, you double the concentration. Yeah, that's getting reaction orders. If you double the concentration at the second order, the rate will quadruple, okay? So yeah, in all of those, my point is you have to get to reaction orders by experimental data. Now, molecularity, so hold that thought. Molecularity is basically how many particles in your, molecularity only applies to, this is my behind the scenes, molecularity only applies to elementary steps. And basically it says how many particles are participating in that elementary step. That's called molecularity. Okay, so molecularity, we're going to focus on the particles on the reactant side. We don't care about the product side. Here are these prefixes that we all like to kind of throw. Una, like unicycle, is one wheel. Unimolecular means one particle participating in that elementary step. A bicycle's got two wheels. Bimolecular means you have two particles participating. A tricycle has three wheels, and so trimolecular or termolecular, they're the same. Means that for that elementary step, you have three particles, and I'll kind of touch on this. You have three particles that are actually bonding each other and proceeding in that elementary step from reactants to products. Termolecular, trimolecular. Okay, so an example of a unimolecular step, like unibond, unimolecular, now, would be this, where A goes to form B, or A decomposes into form B and C. So unimolecular, we're just looking at the reactant side. Bimolecular, we have some options here. You have two different types of particles that are finding each other to go to form something. In this case, we have two of the same particle needs to react to go to form something, you know, and there are more options here. Notice that actually the second and the third to me are the same thing, aren't they? I think. Okay. So these would be behind the scenes. So we're talking about the molecularity. Unimolecular, bimolecular. Termolecular, I mentioned three particles. Again, there's different possibilities here, but the one I have here is you have one particle of A react with two particles of B. That makes three, go to form C. Now, Termolecular or trimolecular, and this will actually come into play when you're kind of evaluating a mechanism. Remember, mechanism is a set of elementary steps. If your elementary step has 3 particles, termolecular, it's probably potentially suspicious. Okay, and like I said, the reason is that it's kind of like trying to round up cats. You know how you're like trying to get cats in the same room at the same time? Well, picture your 3 wildest cats and try to get them in the same room at the same time. So if we see something that's termolecular, actually probably it's really actually, instead of 1 step, it's 2 steps. And I'm giving an example down here. So it looks like this. What if instead of 1 of A and 2 of B going to form C, what if it did it this way? 2 of B goes to form D, and then that D reacts with the A to go to form C. Now, we have added equations before. Let's just go ahead and add them, see what we get. The way this works is I'm going to put my reaction arrow down here, and notice that my D appears as 1D on both sides. So I'm going to go ahead and cancel it off. D here, in a minute, we're going to actually call that an intermediate because it kind of appears behind the scenes, but it doesn't appear in the overall reaction of interest. And then we go ahead and add what we got. So if we add 1 plus 2 now, yep, I'm looking at A plus, oops, wow, A plus 2B goes to form C. So I'm just kind of telling you that's kind of probably what's more likely. Well, this is what, bimolecular? Is this what bimolecular? Is it both bimolecular? So one of the things that I just talked you through is what's been important is if we have A plus B going to form C, we came up with the rate law expression is equal to rate law constant times the molar concentration of A raised to its reaction order times the molar concentration of B raised to its reaction order. You just told me these we can get from graphing or we can get from observing, looking at data, but these are gotten from data. Now, let's see what else I got. The reaction order of an elementary step, the reaction order, the superscript, actually does come from its molecularity. Another way to say what its molecularity is its molecularity, if you think about it, kind of the example, is its stoichiometric coefficient. So it does come from there. If what you're dealing with is an elementary step, we can write a rate law expression for all of our elementary steps, and we can just pick off their stoichiometric coefficient or pick off their molecularity to know what the reaction order is, if it's an elementary step. For instance, if this is an elementary step, check out the heading, elementary step, not a reaction of interest. Then we can use the molecularity of A, which is unimolecular, to know that it's first order with regard to A. We can, for that elementary step, write out a rate law expression. You see why I hesitate with all this? Because otherwise, you cannot look at an overall reaction of interest and just pick out the stoichiometric coefficients using molecularity to come up with a reaction order. You can't do it. You spend how many weeks saying how you come up with M and N. But if it's an elementary step, you can. All right, so let's look at another example. So elementary step, 1 particle of A goes to react with 1 particle of B to form C. They're both unimolecular, they're both first order because it's an elementary step. All right? About this one, what order would A be? Second order, yeah. Because it's an elementary step.
If we take the overall chemical reaction and break it down into elementary steps and then
Yes. Yep. She's saying, and I'll kind of show you a trick in that. What she's saying is if you know the elementary steps and you can use molecularity to get to those rate law expressions, how do we then use that information to get to the rate law expression for the overall reaction? And yes, but there's a few tricks. Yep, you got it. You got it. And here's probably the biggest trick in that. So this is where I like to say, you know, if you're a family of 5, like some of you guys might be, you know, you always have like, you're trying to get out the door. Say I say it's Christmas time, you're all in the house. You have that one person that's a little bit slower than everybody else. And that person who's slow is gonna actually set the tone for whether you make it to Christmas, your Christmas gathering on time. Okay, so that's the rate determining step. It's the slowest, and it basically says, this is how fast you're going. I'm sorry, but you guys might have been ready 30 minutes early, but if that one person's gonna be 30 minutes late, everybody's 30 minutes late. It happens, rate determining step. So then, if we are to peek behind the scenes, look at all those, what we're gonna end up doing is we're gonna focus on that slow guy. That slow step, and as it turns out, that slow one, whatever that rate law expression is going to actually, in some cases, be our overall reaction of interest, that rate law expression. Okay? It's kind of what it's going to building up to. The rate determining step is going to be what governs the overall rate law expression. The rate determining step is sometimes called the rate limiting step. Rate determining step. Okay. So you could do a couple different ways. I mean, if you have a list of 5 elementary steps here, if your slowest one is the first step, then basically it goes way, fast. Okay? If it's the last step, it goes fast. Way, then you're done. Okay, so those are, you know, kind of how that works. I already mentioned an intermediate. The D was an intermediate before. It is definitely something. It's a thing, so they say. Okay, but that D was created in the first elementary step and consumed in the second elementary step, so it doesn't appear. Okay. Sometimes something like D is what we say isolatable. Sometimes wouldn't that be fun to have a job where you're like, I'm going to grab D before it gets consumed by the second elementary step. Sometimes it isn't isolatable. Okay. So now we're kind of adding to our understanding of your rate law expression. Rate is equal to K times the molar concentration of your reactants raised to the reaction order. Okay. So we propose a mechanism for this reaction, and the mechanism has to, like the 5 steps or whatever, have to make sense. They have to make sense with what we start with. They have to make sense with what we end with. They have to make sense with what the overall observed rate law expression is. And they have to make sense if we're going to add something to our chemical reaction, like an inhibitor or a catalyst. They have to make sense. They must make sense. Thou shalt not lie. So mechanisms. Mechanisms are behind the scenes of what's going on for an overall reaction of interest. Like I said before, though, sometimes, and it seems kind of oxymoronic, that your mechanism behind the scenes is only one step. And if you're like, well, Mrs. Snipes, if it's only one step, then that step needs to match my overall reaction of interest. And you're totally right. Okay, you are totally right. An example of a reaction whose mechanism consists only of a single step. So you're going to get excited here. If it consists only of a single step, we can use molecularity to get to the rate law expression for that elementary step. And then that rate law expression for the elementary step will be the overall rate law expression for that reaction of interest. So one step, and somebody has to tell you this. Sometimes students get into this material and they're like, well, how would I know? Well, there are certain different types of problems you might run into, but I'm telling you this happens in only one step. So a new term for me is concerted reaction. If you ever heard the word concerted reaction, that means that behind the scenes, that your reaction of interest only occurs in one elementary step. Okay. So concerted reaction, I like the term elementary reaction. Elementary reaction also means that there's only one elementary step. Makes sense. Okay, so yeah, so this kind of in red says what I said a minute ago. If you're like, well, if there's nothing added to this and you get this, okay, your elementary step is gonna have to be a reaction of interest. And you're totally right. So now I have a series that are kind of, I don't know, I find them, my slides kind of irritating at this point. But this is all just showing you different ways of looking at N2O plus NO. Goes to form, and this is, I have a slide to kind of talk about this, but this is actually what we call a transition state. Here in a minute when we see an energy diagram, this is going to be kind of at the peak of your activation energy. You kind of see those two little dotted lines, which is itching to go to form products. Okay, and then this is the products that form N2 and NO2. Showing the same thing. Okay. There's a transition state. I just think I'm overboard on this. This one's a good one though. So for the elementary reaction that we've been talking about, here's your energy diagram. So of course we have energy along the y-axis, along the x-axis, kind of think of time. We've looked at this one before. We call this what the activation energy, this little hump right here. Okay, the fact that your reactants that are higher energy than your products, this must be an exothermic reaction from left to right, as indicated by the negative delta H. These are all things we've talked about. This is showing the reactants, this is showing the products, and this is the transition state. So the transition state is kind of at the top, like I said, of the energy barrier. Now, if you're like me and kind of hear new terms, there's definitely a difference between the transition state or activating complex and an intermediate thing. Two different things. Totally two different things. All right. So back to how we come up with the rate law equation. All we got to do is focus on the elementary step and use molecularity. We said if it's an elementary step, we can use molecularity. The coefficient, we have one particle of N2O reacting with one particle of NO. They're first order. Okay? So that actually is our rate law expression, just because it's an elementary reaction. This was funny. I was getting ready for today's lecture. They just look funny. These are HI molecules. Okay, here's the transition state, and it's actually the molecule HI is going to decompose to form a molecular hydrogen, molecular iodine. This is an example of another elementary step, or excuse me, an elementary reaction, which means it only occurs in one elementary step. Since it only occurs in one elementary step, we can kind of limp out. This is an elementary step, we can use molecularity. It's first order with regard to, it's second order, wouldn't it? We have two HI molecules, it's second order. So, you good with that? Okay, second order. Okay, so now I need to spend a little bit of time talking about the reality that there are reactions out there that occur in more than one step. So the first one we're going to look at is we have an initial slow step and a fast second step. Initial slow, fast second. So what I said a minute ago is to, and you're going to see these two elementary steps add up to the overall reaction of interest. We need to focus on the slow one, to the rate law expression that's brought to the table by the slow one will govern what the overall rate law expression will look like. So here we go. Now, right off the bat, you probably know that this can't be, can't just be one elementary step because it would make it term molecular. Does that make sense? Let me have that in here. So term molecular won't work. So what this second paragraph is saying is that went ahead and for whether we did a graph or whether we did kind of doubling the concentration, only the other's the same, or the other one the same, we got a reaction order of first order for H2 and first order for ICL. Okay, so this actually is the overall rate law expression for the reaction of interest. First order with both of them. So again, you know that it occurs in more than one step because we're not using molecularity, are we? Molecularity would be what? First order with H2 and second order with regard to ICL. That's not the observed rate law expression. So this actually then is a proposed two elementary steps to get the reaction of interest. I told you the first one's slow. Here's the first one. Notice that what we produce, we take one particle of H2, one particle of ICL, and we get one particle of HI and one particle of HCl. And then the fast step takes that particle of HI and react with another particle of ICL to form one particle of H2 and one particle of HCl. So if we add them up together, like we've been talking about doing, notice what cancels. What will cancel there? Yep, the HI will cancel. If you can ever kind of do that, actually the HI is an example of an intermediate. Goodness, not writing. Intermediate. Goodness gracious. So one check to see if your mechanism, if your set of elementary steps is correct, is do they add up to be equal to the reaction of interest? And the answer is yes. The other check is to focus on the slow step, which is step one, to use molecularity, and I can't remember what my builds are like, to come up with the rate law expression for that elementary step. So for step one, I'm going to say rate 1 because it's elementary step 1 is equal to rate law constant K1. And since it's an elementary step, I can go ahead and use molecularity. We have one, the molecularity H2 is 1. So I'll put a 1 there, first order. The molecularity of the ICL is also 1. See how that works? Slow step, focus, come up with the rate law expression using molecularity for that elementary step. And the one thing that's different here is I probably would put rate 1 just to kind of remind myself I'm dealing with an elementary step. And in this case, it matches. So you see what I mean by saying matches? This actually using the rate determining the slow step, elementary step behind the scenes matches with what's observed for the overall reaction. So that's another check, an important check. So we could say then the rate, the overall reaction rate is equal to K, where K actually is K1 for the first elementary step, times the molar concentration. H2 is the first power, and molar concentration of ICL is also the first power. Energy diagram. So we start with reactants here. Okay. The reason you see two humps, okay, is actually because there's two elementary steps that are happening. We have the intermediates between the two elementary steps. Remember that HI was an intermediate. So we have an activation energy. We have this would be your delta H for the first step. This would be your delta H for the second step. Elementary step. This would be your delta H for the overall reaction. Basic slide, isn't it? This would be your activation energy for the first elementary step. And this cute little thing would be your activation energy for the second elementary step. Now, I don't know what your test isn't made yet. If it was made, I wouldn't tell you what's on it. But every once in a while, I will have, for this unit of material, an energy diagram. It looks like this. And so this is actually the same thing. Let's see. The overall, is it endo or exothermic? What do you think? Exo. Yep. All right. Well, let's look at another example. In this case, it's going to be, again, a slow step followed by a second fast step. Here's the overall reaction of interest. And the observed rate law expression looks like this, where it's second order with regard to the NO2 and zero order with regard to the other reactant, CO. And we talked about if you raise anything to the 0th power, that's 1. So the overall rate law expression is K times the molar concentration NO2 raised to the second power, second order. Well, we know it doesn't happen in a single step. If it happened in a single step, we could use molecularity, right? If it happened in a single step, we could use molecularity. It would be first order NO2, first order CO. And that's not what's observed. And we'll X that. Okay? So that'd be too easy. So a proposed mechanism might be this. But let's check it out. What if it goes this route? 2 particles of NO2 for your first elementary step proceed to form NO3, which is not in your reaction of interest, and NO. The second step could go like, and that's slow. That's important. That's rate determining. And you already kind of see where this is going. That's rate determining. We can use molecularity, where you're back to your NO2 being second order for this elementary step. Well, then after that, your NO3 reacts with your CO2 to form NO2 plus CO2. Each one of these elementary steps you're already counting this need to be a balanced equation, right? So is there anything that can cancel here? The NO3 can cancel. Yep. And one of the NO2s. Yep, I agree. And one of the NO2s. You got it. So if we bring things down that didn't cancel, we end up with 1 unit of NO2, 1 unit of CO, And on the product side, we have NO left over and CO2, which is the reaction of interest. So again, there's a couple of checks here. That's one of the checks, is do those elementary steps give you the reaction of interest? The answer is yes. And the other step is if you focus on the rate determining step and then go ahead and use molecularity, does that match up with what you observed? And the answer for that is yes. So again, I probably would call this rate 1 because it's the rate law expression for the first elementary step is equal to the rate law constant K1 associated with that elementary step. Using molecularity, the molar concentration of NO2 raised to second order because it's second order. So yeah, since, it all matches. It's just more of a confirmation than anything. So some semesters, my exams for this unit look like this, where I well, here's a mechanism, and here's a mechanism. What do you think? Do any of these mechanisms fit the bill? So there's a couple different checks you can do. Yeah, I'm gonna hold off on this one. So we will pick up here, if it's okay with you guys. We're running start at it on Monday. But don't forget everything that we talked about.